This is a cinematic birth of our solar system. From a collapsing cloud of gas and dust came the sun, the planets, and eventually, us. Tonight we travel back to the beginning and follow that incredible journey right back to Earth. 9 billion years after the Big Bang, in an ordinary spiral arm of an ordinary galaxy, there is a cloud. Not a cloud of water vapor, a cloud of gas and dust, light years across, cold enough that its clouds within clouds fold in on themselves in near total darkness. Somewhere inside it, in a pocket no wider than a fraction of a light year, the raw material of a solar system is waiting. It has been waiting a very long time. Nothing here is moving toward becoming anything, yet. Then something tips the balance. Maybe the shock wave from a nearby supernova. Maybe just chance, a fluctuation, a slightly denser knot, gravity finally winning an argument it had been losing for millions of years. The core begins to fall in on itself. As it does, it spins faster, the same principle that pulls a figure skater's arms in tight, and the collapsing gas begins to flatten, venting some of its energy outward as twin jets, punching through the materials still falling in. At the center, pressure and temperature climb past anything else in the cloud. This is a protostar now, not yet a star, not still just gas. It brightens in fits and bursts as fresh material rains onto it. Around it, the leftover gas and dust that didn't fall all the way in are settling into something new, a disk. This disk, the solar nebula, is almost entirely gas. The solids that will eventually become planets are, at this point, less than 1% of its mass, drifting through it like dust in a sunbeam. It is hottest near the newborn sun and colder toward its outer edge, and that temperature difference matters more than almost anything else in this story. It decides what kind of material can exist where. For scale, if the whole disk were the size of a dinner plate, every planet that will ever form from it would fit inside a single grain of salt at its center. As the hot gas near the young sun begins to cool, the first solid grains condense directly out of it, minerals that only exist at very high temperatures. Some are swept up almost immediately into compact, glassy droplets called chondrules. Exactly how chondrules formed is still debated. A shock wave through the disk, or violent collisions between growing bodies, are two of the leading ideas, and this film shows one without ruling out the other. Farther out, past an invisible boundary called the snow line, it's cold enough for ice to condense too, and that line isn't fixed. It moves as the disk evolves for millions of years. Growth starts small, smaller than small. A single silicate grain, drifting, touches another. They stick, not through gravity, which is far too weak at this scale, but through the same static electric forces that make dust cling to a wall. Collision by gentle collision, these grains build into loose, fluffy aggregates, fragile and porous, nothing like solid rock yet. The disk is not calm. Turbulent eddies stir the gas at every scale, and different-sized particles respond to that turbulence differently, which is exactly what lets some of them find each other. Meanwhile, gravity is doing its slow work too, pulling the growing aggregates down out of the gas-rich upper disk and toward a thin, solids-enriched layer at the midplane. Millimeter by millimeter, the aggregates compact into pebbles, irregular, non-uniform, nothing like the smooth spheres of popular imagination. Beyond the snow line, icy pebbles form alongside their dry, rocky counterparts. And now these pebbles are large enough to start decoupling from the gas around them, which sets up the central problem of the next two chapters. Here's the problem nobody expected. Pebbles shouldn't survive. The gas in the disk orbits slightly slower than a solid particle would on its own, so every pebble feels a constant headwind, a drag that steadily steals its angular momentum. Larger pebbles drift inward fastest, spiraling toward the sun over just a few hundred orbits. In a race, some particles win and others lose. And even the ones that don't drift away hit a second wall, collide too gently, and pebbles just bounce off each other. Collide too hard, and they shatter back into dust. There is a narrow, stubborn gap between too gentle and too violent, where almost nothing manages to grow. By the end of this chapter, the disk is full of pebbles that have simply stalled. But the disk isn't uniform, and that turns out to be the way out. Local pressure bumps, at the edges of gaps in slow-moving vortices, act like eddies in a river, and pebbles drifting from both directions pile up inside them. The snow line adds a second trap of its own, where icy pebbles pile up just past the boundary where ice survives. Slowly, several separated zones of the disk begin concentrating solids far above the average. This is where the stalled pebble problem finally breaks. Inside one of these concentrated regions, something changes. There are now enough pebbles, packed closely enough, that their combined mass starts to push back on the gas around them, instead of the gas simply pushing the pebbles. That feedback lets pebbles collect into long, dense filaments. Filaments draw more pebbles in. And once a filament is dense enough, its own gravity takes over. The whole structure collapses. Not by grinding pebble on pebble together into something bigger, one collision at a time, but all at once, an entire concentrated swarm collapsing directly into a single body. In one step, this process skips the growth barrier that stalled Chapter 9 entirely and produces a body tens to 100 kilometers across, a planetesimal. already far larger than anything that came before it. That's the key idea worth pausing on. These bodies are born big. There is no intermediate boulder stage, no smooth ladder from pebble to planetesimal. Streaming instability manufactures large bodies directly, scattered across the disk in uneven batches, some far larger than others from the moment they're born. Not every planetesimal has the same future. Buried inside many of them is a radioactive isotope, aluminum-26, left over from a supernova that seeded the birth cloud long before any of this began. As it decays, it releases heat, and in a planetesimal that formed early enough, while that isotope is still abundant, that heat is enough to melt the interior entirely. Metal sinking to form a core, lighter rock rising to form a mantle. A planetesimal that forms only slightly later has missed the window. There isn't enough aluminum-26 left. It stays cold, primitive, and undifferentiated, permanently. A fossil of the solar nebula's earliest chemistry, standing right next to a fully differentiated neighbor of the same size. Among a swarm of otherwise comparable planetesimals, a handful begin to pull ahead. A larger body's gravity doesn't just attract nearby material in a straight line, it bends the paths of anything passing close by, focusing infalling debris toward itself far more efficiently than its smaller neighbors can manage. And the bigger it gets, the stronger that focusing effect becomes. It's a runaway. A few bodies growing dramatically faster than everything around them, entirely from being slightly larger to start with. Runaway growth doesn't run away forever. As an embryo grows, it stirs up the smaller bodies around it, literally raising their orbital velocities, and that faster motion works against further gravitational focusing. The result is oligarchy. Not one winner, but several embryos of comparable mass, spacing themselves out at regular intervals across the disk, each still surrounded by smaller planetesimals that haven't yet been swept up. Embryos keep growing two different ways at once. The old way, discrete, chunky collisions with planetesimals, never stops entirely. But there's a second channel, pebble accretion, where gas drag lets an embryo capture drifting pebbles across a radius far larger than its own gravity alone would allow. In the outer disk, feeding the giant planets, pebble accretion is the dominant channel. That much is well established. Inner in the terrestrial zone, though, which channel actually did more work is still an open, contested question. This film shows both operating side by side, because that's what the evidence currently supports. Everything changes once you cross the snow line one more time. Out here, ice roughly doubles the mass of solid material available, compared to the same distance closer in. Icy pebbles drift inward and pile up at that boundary, just as before. But now there's simply more raw material to work with. This reservoir is what's about to build something the terrestrial disk never could. Beyond the snow line, an embryo begins pulling in that icy pebble stream, growing steadily. Individual pebble impacts giving way to a smooth, continuous accretion stream as its gravity and its puffy, extended atmosphere both grow. By the time it reaches somewhere around 10 to 20 Earth masses, it has carved a pressure bump of its own into the disk, pebbles now visibly diverting around the very core that used to capture them. Once a core is massive enough, it can hold on to more than just solids. It starts pulling in the hydrogen and helium gas surrounding it, forming a small bound envelope. At first, this is a slow, patient phase, the envelope compressing under its own weight for a long stretch of time. But once the envelope's mass catches up to the cores, everything accelerates. Gas pours in from across a wide stretch of the surrounding nebula, and a gap opens in the disk, a dark, planet-carved annulus, visible on a nebula-wide scale. What emerges is oversized, still glowing from the sheer energy of its own formation. Jupiter. Farther out, the same story plays out on a slower clock. Solids at Saturn's distance take longer to assemble into a core, and by the time that core is ready to pull in gas, the surrounding nebula has already begun thinning. Saturn's gas streams taper rather than shutting off sharply the way Jupiter's did, its growth ending not with a dramatic gap cutoff, but simply fading out as the local gas supply runs low. The result is unmistakably related to Jupiter, and unmistakably smaller. Uranus and Neptune are a harder case. Did their cores grow slowly in place, out where orbital timescales stretch for centuries? Or did they form closer in and migrate outward afterward? Both are live hypotheses, and this film shows them side by side rather than picking a winner. What's not in question is the outcome. By the time the gas disk finished dispersing, these two had only managed to capture a comparatively small envelope each, leaving them with a different internal structure than their larger siblings. No sharp boundary between core and envelope, just a smooth gradient from one into the other. 4 giant planets now stand in a clear size hierarchy: Jupiter, then Saturn, then Uranus and Neptune close behind each other. Planets don't necessarily stay where they're born. A planet embedded in a gas disk carves a spiral wake in the material around it, and that wake can push the planet's orbit inward or outward, a well-established process called migration. 2 planets whose orbits fall into a clean ratio can lock together and migrate as a pair. One especially striking idea, the grand tack, proposes that Jupiter migrated sharply inward before reversing course entirely, dragged back outward by a newly formed Saturn. It's a compelling model, but recent simulations put its odds of actually happening below 50%, so we show it as exactly what it is: one contested possibility, not settled history. A later chapter of instability among the giant planets' orbits, sometimes linked to a late heavy bombardment of the inner solar system, is also still being actively revised by current research, and its timing is treated here as genuinely uncertain, not fixed. The young sun's own radiation starts eating away at the disk that built it, heating outer gas until it's stripped away entirely, then working inward. As the gas thins, the aerodynamic damping that once kept planetesimal orbits calm starts to fail, and eccentricities begin to rise. The pebble supply, once a continuous drift, thins to nothing. By the end of this chapter, the terrestrial region is a bare field of embryos and planetesimals, with no more gas left to keep the peace between them. Without gas to damp their motion, dozens of Moon to Mars mass embryos begin crossing each other's paths. Orbits stretch. Some encounters are close calls, tidal distortion, then a near miss, an orbit abruptly redirected rather than ended. Others aren't close calls at all. When 2 embryos finally do collide, this isn't a fireball in the movie sense. There's no air here to carry a shockwave, no atmosphere to burn. It's raw, kinetic energy, converted directly into heat. Molten ejecta arcing outward on ballistic paths, some of it escaping, some of it falling back to slowly reaccrete onto whatever body survived the impact, larger now, and reforming toward round. This is how Earth and Venus actually finish assembling. Not gently, but through a series of these violent embryo-scale mergers, each one releasing enough energy to partially melt the impacted body. Not every encounter ends in a merger either. A hit-and-run graze can send an impactor looping back onto a new, more eccentric orbit rather than sticking. By the end of this chapter, the inner solar system has thinned to a handful of much larger, still-forming worlds, their surfaces glowing with magma oceans. A note before this chapter: the exact size, angle, speed, and even the number of impactors involved in the event that formed the Moon are not definitively known. What you're about to see is one illustrative reconstruction built from one family of leading models, not a documented record of what actually happened. Several competing pictures remain under active study. With that said, here is the model. A body roughly the size of Mars, on a slow collision course with the still-forming Earth. Tidal distortion as it closes the final distance. Contact. And for a brief, cataclysmic period, the two bodies partially merge, mantle materials stripped away and flung outward in an immense, expanding plume. That debris begins organizing into a ring around the young, now largely molten Earth. Within it, clumps grow, competing moonlets spreading across the Roche limit, until material accreting from that debris disk finally consolidates into a single, dominant body. Two worlds emerge from the wreckage, a battered, still hot Earth, and beside it, for the first time, a moon. Earth's surface begins to cool, the magma ocean starting to crystallize into solid crust. Above it, the moon is accreting from what's left of the debris disk. How quickly is still debated, with estimates ranging anywhere from months to centuries depending on the model. But however fast it happened, it ends with a moon sitting far closer than the one we see tonight, and much larger across the sky. Earth's interior is still settling too, continuing to differentiate in the impact's aftermath, inside a solar system that is still strewn with debris. The giant impacts are mostly over, but smaller ones continue. Quieter now, a slow rain rather than a bombardment. This late accretion is one candidate explanation for why Earth's mantle still contains trace amounts of metals that should, by rights, have sunk entirely into the core during differentiation. Not everything found a planet to fall onto, though. What remains between Mars and Jupiter isn't a planet that failed to form. It's a belt kept dynamically excited by Jupiter's gravity, its orbits stirred into eccentric, inclined paths, grinding against each other rather than merging. Resonances with Jupiter carve clean gaps through it, the Kirkwood gaps, while far beyond, in the cold outer disk, an entirely separate population of undisturbed, primitive planetesimals waits, untouched by any of this inner system violence. The four giant planets, meanwhile, are still finding their final arrangement. At some point, historically proposed around 400 to 700 million years after formation, though some current research argues for a much earlier timing, and the debate isn't settled, their orbits cross a set of mutual resonances and destabilize. The outer disk of remaining planetesimals gets gravitationally scattered outward, feeding the Kuiper belt, the scattered disk, and the distant Oort cloud, while some material is flung out of the solar system entirely. When the dust settles, almost literally, the giant planets have reached the wide, well-spaced configuration we still see today. Pull back. Four giant planets, widely spaced, calm now after everything that built them. Closer in, four rocky worlds, an asteroid belt between them and the giants, everything at last in its correct relative scale. Pull back further still, and the entire architecture sits against the same galactic backdrop this story opened with. The same spiral arm, the same ordinary neighborhood of an ordinary galaxy, 4.5 billion years on. It didn't have to turn out this way. Nudge the timing, the masses, a single early collision, and none of this is quite the same. This is what's left standing after everything that could go wrong mostly didn't.